I'm a PhD student. My name is Fabiano Della Justina. I'm working in Madison area, focused on gravity modeling, 2D, 3D, forward, inverse modeling, all of this kind of modeling. And I'm in the last year, doing my last year as a PhD student. And yeah, so good to go my presentation. So today I'm going to present about the incorporation of geophysical, petrophysical, and geological constraints in gravity modeling to resolve structures at depth. So it's well known that mainly gravity and magnetic data, when you are performing a model, we have to constrain in order to have a more reliable model. But how important is to incorporate this information to the gravity model? So I'm going to show you how these incorporations may enhance, refine, or modify the model. Because as I mentioned before, a gravity model as well as a a gravity anomaly as well as a magnetic anomaly may be generated by many different models with a variety of combination of source location, source geometry, and petrophysical property, what we call non-uniqueness. So the incorporation of geophysical, petrophysical, in this case density, and geological data or information into the modeling can be forward or inversion model or combined, can result in different models. So I'm going to provide an example from Madison area, focused on the porcupine assemblage, which the external contact of this assemblage coincides with two main faults. And I'm going to show you from the progression from a very ordinary, purely unconstrained inversion to a more sophisticated geometry inversion. So just a quick review about forward modeling, inverse modeling, because we're gonna talk a lot about this. So let's say the big difference between forward and modeling, we can start from, let's say, the same start model, and by changing either the densities or the geometry, step by step modify, we can get a good misfit at the end. Here's the dots are the data, the observed data, and the black line is the predicted data. So when you get a good misfit, we have a good model. And inverse modeling is the idea is the same, but the hard work, the algorithm, we let the algorithm do this. So we have the start model, and by after a couple or dozen of iterations, we get the final model as good as in the forward modeling. So, but in this case, just for illustration, are the same, but pretty much they wouldn't be the same. And as I mentioned before, the petrophysical information, the properties that connect your model to the data is dense in the case of gravity modeling. And the geology. So this is the geology at the Madison area. So it's quite diverse, but we will be focused on this area, the porcupine assemblage. So we can see that because the contact of porcupine assemblage and this case the made between intermediate metavolcanic rock at south and also at north, they just coincide to the two main faults in that area. So it allowed us, because we have density contrast, that area is allow us to modeling the fault as well. So also on the right here, we have a more simplified geological map. So is the map that I'm going to use for my modeling. And also we need the gravity data. And for this presentation and for all of these models that I'm going to present, so we got a combination of GSC data here in this map on the middle in red, and in blue is Metal Earth data that we have acquired. So the Metal Earth data is 300 meters apart, and stations 300 meters apart, and the uncertainty is it's very good. Actually, 0.2 milligauss, and while for the GSC data is 1 milligauss. So we combine these two data sets, and we have this gravity map on right. And so the first model that we have, when you have the data, we don't have any other information, we start from an unconstrained inversion. So this model, so here, this bigger one, we have the gravity data just overlaying this model. In the smaller one figure, we have the geology and overlaying. So the model is the same, just the palette colors is different, but it's the same. So the Porcupine Desert Fault is here in red, and the Pipestone Fault is in blue. So here on the bottom we have dimension, the resolution, the voxel resolution. And so in this case we have a model, but we don't have any control over the density problem because it's just based on the start model. We don't have any control over source location, or source geometry. So it's a model, but it's more like for familiarize with the data. But now we have new information that from this case from Discover-BTV, this interpretation suggests that these reflectors, the strong reflectors on here, is the bottom of the Porcupine assemblage. So now we have an idea of the depth, the thickness of Porcupine assemblage. So as we have this information, we can, doing some depth weighting, we can, by adjusting in this equation, the value of Z0, we can have a good match between this interpretation and our model. But okay, now we have some control over the source location, but still we don't have any idea over the source geometry and also the density problem. And but eventually we got some samples of the Porcupine assemblage, some core samples, and we could estimate the density of the Porcupine assemblage. So, and now we can combine depth weighting plus density property. So, and at least for the Porcupine assemblage. And now, by adjusting the value of Z0 and also the start model density, we have a kind of control over the density problem for Porcupine assemblage only, and also the source location, which means actually how thick it is the Porcupine assemblage. Now we're going to stop invert the data, and we're going to do some forward modeling. Here we have the Porcupine assemblage, and at A, B, C, D, we have actually seismic sections. B, C, D are Metal Earth seismic section, and A is Chillington line from Discover-BTV. So now we combine density data. So we have we have also density data from Lower Teesdale, which is south of the Porcupine assemblage, and also Kidimuru at north. So, and also geological map, you're going to constrain at the surface geology and also seismic sections. So, and by doing this forward modeling, we have this 3D shape of the Porcupine assemblage here on the bottom of my slide, right. And so now we have the shape, the geometry of Porcupine assemblage. So we can invert this data doing a geometry inversion. And we also we incorporate more density, the whole compilation, the Metal Earth compilation, which we can see here, the geographical distribution on right. And it's a good coverage. And we combine these 2D models combined with this petrophysical and doing geometry inversion, we came up with this model. But we have another important thing to point out. Actually, for having this model, we have to constrain we have to fix the contact, the external contacts of the porcupine assemblage, because otherwise we would have something like this. And this model, it has not a good misfit as this one, and also it doesn't make any consistency with previous interpretation. So we also have to fix the external contacts of porcupine assemblage. We didn't incorporate, we just have to do something during the version. We didn't incorporate any other data, okay? But at this point, we have a better control of the density problem, because we incorporate not only the porcupine assemblage density information, but also the whole area. And also we have control over the source location, and also something that we didn't have before was the source geometry. And okay, we can say, okay, now we have, let's say we have a good model. So let's get this for the final model. But guess what? Maybe not, because we cannot deny that in the seismic section, we still have a strong reflector underneath the porcupine assemblage. So in this map, we have a view below from, we have, this is Timmins area, and here is the Shillington line, and Valganier, Warabig, and Madison. So we have this strong reflector. And it, according to this paper from last year, actually this year, sorry, and we was interpreted as Deloro, could be Deloro. So the Deloro could be a hypothesis right now. We have to test this hypothesis. So, and Deloro is outcrops here in Timmins. So we have to test this, because Deloro, the dense Deloro is lower than the lower Teesdale, which is located above Deloro. So it could have effect in the porcupine assemblage depth, and maybe in the geometry. So we have to check this. So here we can see at Shillington line how would be porcupine assemblage without Deloro, without having Deloro underneath. Meaning you have taken into account Deloro, and on the bottom something in a 2D for Shillington line if you take into account Deloro. So it will be the difference will be the thickness, right, of the lower assemblage. So it could be more similar to the previous interpretation. So here just a 2D forward modeling for Shillington line. So as we can see in comparison, when we don't take into account Deloro, we just say, okay, it's just don't have any, it's just a single unit below porcupine. So the huge difference will be the depth of porcupine assemblage, like the bottom, the depth of the bottom, the thickness, and also a little bit about the geometry. So okay, both have a good misfit. So in terms of 2D at Shillington line, both could be good models. Let's see in 3D. And what I did was just have this 3D model as a start model. Okay, we have actually to make the area smaller, because this is the Madison whole area. Now we have a smaller area because the place where you have seismic sections. So this area is now before was 25 kilometers. The thickness of the model now is 12 kilometers. So it's the start model, and by applying geometry inversion, just allow the basement below the lower to move. So we could have, let's see how will be this model in terms of misfit. So basically we are comparing the porcupine, these two scenarios, like porcupine and Deloro, and the case just have porcupine, and all around will be the intermediate to mafic volcanic rocks. And we have this as a result of this 3D geometry inversion. So we have this Porcupine, Lower Tisdale, Kinmurun, and Deloro. So in a slice, and here is not in a 3D. So it's okay. The misfit was the goal. Just remind you, the goal was 1 milligal because it was the GSC uncertainties for this data, and we have 1.8 milligal. That's not that bad. And so in comparison, just the observed data and the predicted data and the residual. So now we have, as before, actually, in terms of density problem, we have a good control. But in terms of source location and source geometry, we have a better, we resolve better this over source location and source geometry. And when you compare the Porcupine assemblage, now the view is, here is Shillington line, and the other side is Madison. So we are looking at east. And so when you compare the lower assemblage just in gray, the lower assemblage has not been included in this model, okay? And when you combine the part in gray and red, the lower assemblage has been included. So what we have here, just to have a good confidence in terms of, for example, in blue is would be the Porcupine Distorfault. So it doesn't change too much in terms of how the Porcupine Distorfault is dipping in terms of angles, just a little at Shillington line, and at Madison actually doesn't change whatsoever, because the interpretation that the lower was horizontal, that part of the area. In terms of pipestone fault, actually doesn't change too much, just become deeper, the bottom of Porcupine assemblage. And as a conclusion, so we have seen this presentation today. So we have a very simple model, unconstrained model, that we don't have any control over density problem, source location, or source geometry. And from this model to get this more model that from a geometry inversion combine incorporate a lot of constraints. So we have a good control over all of these elements in the model. But you can keep going. If you have extra information, we can keep going and refine this model. If you have an exploration program, we can have better results. So as a conclusion, the incorporation of geophysical, petrophysical, and geological constraints is essential to work towards a more realistic model. And due to the non-uniqueness of gravity data, each type of constraint might be more suitable to resolve each type of addressed problem: petrophysical, source location, and source geometry. And a preliminary model like this one on left can be different substantially to an advanced model like this in right. And it's something that the main conclusions of this presentation. So it's everything that I had, pretty much.
Great, thank you, Fabiano. We have time for one question. I got one. Fab, you may have said this, but what was the density difference between Deloro and Tisdale?
The density is not, the contrast is not that much. Actually, this interpretation rely on the fact that at the top of the lower we have iron formation. So that's the point for have that reflector. So that's the interpretation. So
okay, and so that density difference is enough to account for the gravity profile.
Yeah.
Okay. All right. Well, thank you, Fabiano.